Okay, thanks for for an excellent conference. So this talk is maybe a little bit different from some of the other talks we've seen today, and the focus here is really on going back to maybe some old ground, but trying to approach it from a different angle. And many, of course, will know here the sort of long and interesting story of financial models, stochastic financial models. Of course, it's classic theory now. But many of these models lack a closed form for the transition density function, and therefore we can throw out any type of maximum likelihood estimator for calibrating those models to observe data. And when I first came here, I think 3 years ago, I was sort of equipped with some heavy machinery and GPUs, and I sort of managed to calibrate some Hester models by essentially brute force using a least squares error. And that's really rather unsatisfactory for a number of reasons, from a more theoretical perspective, and also from a usability or practicality perspective in terms of stability of the parameters and so on and so forth. And the key idea here is to bring some developments from a financial econometrician who I'll mention in a moment around approximating the transition density under some kind of transformation of the state space. And I'm going to show some examples with univariate and bivariant Markov diffusion processes, in particular the Hester model. And as I was trying to do the Hester model, I thought, well, why don't I just bring across a whole load of code that the author had written in MATLAB and then sort of extend it from there, rather than just having sort of a piecemeal approach. So with that said, I was told to leave any equations out, so the rest of the talk is going to be sort of jam-packed with all this stuff. No, I'm just kidding. But if you know, the original Princeton financial econometrician has sort of obsessively detailed many models, and so it was sort of quite easy really to pull these through into R. And what we're considering is and you know, there is some math here, and I'll try to keep it sort of moving along fast. But we're really considering a class of multivariate time homogeneous Markovian diffusion problems where we have some vector function and we have some volatility matrix. And the key idea by Sahalia was to, instead of trying to find a likelihood function in closed form for the transition density, or find a transition density, he instead performs some kind of transformation of the state variable. Now, just to set notation here and make sure we're sort of all on the same ground, of course, the classic 101 stochastic differential equation is our geometric Brownian motion with our volatility and our drift parameters. And of course, we know this transition function in closed form, and hence the likelihood function. And hence, we can find our maximum likelihood estimator with various different interpretations if you're a Bayesian or a frequentist. And so, without sort of annoying the statisticians too much, and I'm a mathematician, so my apologies there, we can move to the more general case where we now observe our random process at certain discrete times, and we can write down the form of a log likelihood function. And what Sahalia does is transforms X for a nonlinear transformation to a state space where now this transform variable Z is almost Gaussian. And all the rigor that comes with that almost is done for us. And there he then expands the density function using, for those of you familiar with Edgeworth expansions, a very similar approach with Hermite expansions, gets these likelihood estimates in closed form and then inverts the transformation back to the original state space. So that might sound, you know, reasonable enough to do, but that comes with a number of problems as well. So if we stop for a moment here and think about the practical application, and of course this is considered by derivative quants to be much too simplistic still for capturing the kind of shapes of the implied volatility surface that they trade off, but still is a good starting point. We have now a bivariate model, but the problem here, of course, is that one of the variables is not observed. We have a partially observed bivariate Markovian diffusion process. The log stock price given by a diffusion model, and we have a mean reversion process, and we get our leverage effect through some sort of correlation of these Wiener processes. That leverage effect is the crux of the model. One of them. The other one, of course, is capturing the shape of the implied volatility surface. To fit this model is a real pain, as beautiful as it is, and in many ways I think Steve Heston is a genius, but this work really left us with the headache of how to calibrate this model, and of course the parameters here need to be found through either looking at quoted option chains, as we've done in previous work and many others have done, David Ardea also, I understand. And the key challenge, of course, is that this is a horrible problem to solve. You've got some high-dimensional, reasonably not low-dimensional space, and if you try and use least squares error here, you're going to run into a number of problems. And if we were just sort of moving with this framework, which Sahalia gave us, then writing down the log likelihood function would be not so difficult using the approach I described. But of course, the reality is that our state variable is partially observed, and therefore we have to look to the options prices and construct our fully observed state vector G, which is now, we're going to use an at-the-money constant maturity option with the log stock price. And then we can essentially write down our log likelihood function in terms of this observed state variable, not the partially observed state variable, which we come to use through the Heston model. And it turns out that that's quite easy to use. We just need to know what this function is, which maps from our partially observed to our fully observed. And we also, once we have our Jacobian transforming between the two different variables, the fully observed and the partially observed state variables, which in this case turns out to be the vega of the option, all we have to do then is find the inverse of this map between the partially observed and the observed. And so if our function map is given by, takes our unobserved or partially observed state x with the variance and the log stock price and turns it into the log stock price and the option price, we can use any of our favorite numerical pricing methods to then get our price for a corresponding time to maturity strike and our variance and also the log stock price. And so how do we find the inverse of this map? And that's the challenge that we implement in our package. And so our goal is to find the maximum likelihood estimator. We have a set of observed at-the-money option prices. I'm not here trying to fit to the full surface. I'm just looking at the option prices over time. That's a crucial difference from some of the approaches, and it really depends on your application. If you're trying to predict volatility, probably makes more sense to do this than if you're trying to price an exotic option off an implied vol surface. So in our calibration approach, then, for finding the inverse of that map, we take a multi-step approach. The first step is an initial parameter guess within some feasible region. It's not quite as easy as picking a linear feasible region because we have what's called a Feller condition, which is there to preserve the positivity of the variance as that Heston model evolves the variance. But we can pick P in some feasible region constrained by a nonlinear Feller constraint, and for that choice of P, we can then use a standard root finder. We have a convex optimization function and a one-dimensional convex optimization function. And the problem is well defined in terms of giving us, for a choice of P in our model, a 4-vector, the corresponding value of the variance. And from there, once we've got that value of y, and I've put the little p there to denote that it's dependent on our choice of parameter, we can then compute the Jacobian and we can get our log of the transition density function using all the machinery that Sahalia gave us. And if we're just looking at the money options, then we can find the Jacobian, and easily, it's just, again, from a numerical method for the pricing, a numerical pricer. So any kind of FFT-based method will give you a good approximation of Vega. And we've done this at one time step now. And we now repeat this step for all remaining times using the value that we obtain for our variance is to sort of hot start the numerical solver at the next time step. And therefore we can infer a set of variances dependent on our choice of parameter P. And then we can repeat the whole step sort of iteratively using some sort of nonlinear solver, and we minimize the negative of the log likelihood. Now, for geometric Brownian motion, our problem is well understood, and of course we don't need to use any of this machinery, but does serve as a good base case, or for comparison. And we can, in particular, generate the set of data under the exact model, and then see how well the model calibrates. And so if we've got our mean and our volatility, which we fit to the generated data, then we can look at the log likelihood function around that. And one nice thing about using the log likelihood, of course, is you have the Fisher information matrix, which characterizes the curvature of the log likelihood function, and therefore gives you a measure and some indication of how certain you are of the parameter estimates. Of course, log likelihood function has its shortcomings too, in that, sometimes we can get stale regions where the gradient vanishes, or we can have regions where the gradient's very steep. But here we can compare the method where we have our actual parameters, then we can estimate them, and we can compare various different numerical estimates. So we have here our estimated standard error, and we can also use what's called a Huber sandwich estimate as also to measure the robustness of our approximation. And since we know all of this analytically for the geometric Brownian motion, we can quantify or measure our numerical error as well involved in our numerical approximation technique. And so the differences between the maximum likelihood of the actual and the estimated using the package are really quite small. And we can also check the Hessian and the information matrix, where again those are known in an exact form for the case of geometric Brownian motion. Now if we move to the Hester model, then we don't have so much apparatus to measure the performance. Of course, we have the data. We can generate the data under a Hester model, but we no longer have an exact transition density function to compare against, of course. And so here we use an optimization package, NLOptia, and we use a little bit of random seeding as well, and we can arrive at these parameters for our correlation here, our mean reversion rate, a mean reversion level, and our vol of vol. And I think you have to be somewhat careful here in your choice of parameter ranges. So, there are some sort of caveats with using a log likelihood. But in general, it's helpful to see the log likelihood function to give us an idea of how much uncertainty there is in the parameter estimates. And so, in that spirit, we can again look at our Huber sandwich error, or as a measure of a robust measure of our standard error. And again, all of this is done using simulated data and simulating the underlying, and then we use a Fourier cosine method to price the Hester model. And we can look at our error now between the model fitted parameters. So if we now fit the model and simulate the model, we can compare the error in the prices with the simulated prices. So we have our simulated data, we have our Heston prices on top of that simulated data, and then we can fit our model using the calibrated parameters, not the exact parameters used to generate the original data, and we can look and compare how different the prices are over time compared to the known prices. And what we see is a little interesting in that over time, the solution tends to get a little bit better. And this could well be the fact that we don't have a large enough burn-in period when we're simulating. It's not actually, it could be that we erroneously made an initial choice of our initial variance, and hence that error is being carried through. So it's not clear to me why actually the error would go down over time, but it's a fairly subtle effect. So we have then a package. Right now it's sort of living on GitHub. Want to put that into CRAN. And the paper is also on SSRN, so if you're interested in that, there is a link here, and all the details are in that. And we essentially have a number we have the Hester model calibrated, and we have another example models. So our goal is essentially to have a method using maximum likelihood estimation for calibrating a number of stochastic volatility models. And there is much work to do in this, clearly for sort of real-world applications in derivative modeling, where we want to fit to an entire surface and not just be at the money. But I think this is a promising approach, and certainly an alternative to the sort of what I would call standard approach of just using Gauss least error. So thank you.